Hello, everybody. Welcome to our third video on Digital Systems 1. In this video, I will be covering the basics of our logic gates, and, which is here, or, which is here, and not, which is here. So, I will also be covering some truth table basics and some circuit basics. So, let's just get into it. Before I went into like the basic logic gates, I did just want to do a quick binary recap. Okay, so as we know in binary, inputs and outputs can only be 0 or 1. These 0 or 1 binary values can represent a few different things. They could represent low or high. They can represent false or true, and they could also represent off and on. Okay? Now just remember, when I say binary values can represent low or high, what I'm talking about are voltage ranges. So, for example, a 0 in binary can represent a low voltage range, which is normally around 0 to 2 volts, I believe. And then a 1 can represent a high voltage range, which is normally 3 to 5 volts. Okay, so when I say low or high, I don't want you to confuse this with like some exact value. Like these are all ranges. Okay, so now that we've done our binary recap, let's go into logic gates. So before I actually go over our basic logic gates and, or, and not, I just want to talk about quickly what is a logic gate. The way I want you to think about logic gates is I want you to think of a logic gate as a binary rule box where we take binary inputs, and based on the rule that logic gate applies, it produces a specific binary output. Okay? So I'm just going to get right into gates. I think the application will really help you guys understand this concept. So let's start with our first gate, which is a NOT gate. Okay? A NOT gate is also known as an inverter because what it does is it flips binary values. If you input a 0, it'll output a 1. If you input a 1, it'll output a 0. Similarly, if you input our variable a, which could represent 1 or 0, it'll output a prime or a hat. These both mean the same thing. It just depends on how your professor chooses to um, demonstrate it. A prime or a hat really just represents the opposite. Okay? So in this case, if a equaled 1, a prime would equal 0, or a hat would equal 0. Okay? That is the NOT gate, and it is an inverter gate. I'm just going to go over the functionality of the next two gates Then I will go over how truth tables work and how to draw truth tables, and then we will go to some reading combined logic, and then I will go into some university level practice questions, okay? So, this is a NOT gate, also known as an inverter gate. It inverts any input that goes into the gate. The next gate I want you guys to know, right here, it is an AND gate. I'm going to draw this bigger. Is an AND gate, okay? What an AND gate does is it takes two binary inputs, A and B, either 0 or 1, and it produces a combination of their inputs as its output, if that makes sense. It's the AND gate, the rules of the AND gate operate similarly to multiplication. For example, if I input a 0 and 1 into my AND gate, it will produce a 0, and this order does not matter. If I input a 1 and a 1 into my AND gate, it will output a 1, okay? So the functionality of an AND gate is similar to that of multiplication. That is why the output for the AND gate can be represented as AB or A and B. Okay? Now, the third logic gate I'm going to cover is the OR gate. Okay? While the AND gate produces rules similar to that of multiplication, the OR gate is going to apply rules similar to that of addition. So, if I have my binary variables A and B, the OR gate will always output A plus B. Okay? In terms of binary values, this could be 0 and 1 will output 1, just as 0 plus 1 is 1. Okay? Also, in this case for binary, 1 and 1 will just output a 1. There will be no carry or anything. If you've watched my binary addition video, you would know what I'm talking about. Please feel free to check that video out. I cover all basic binary addition, division, subtraction, and multiplication. I also cover the ones complement and twos complement. Okay? So, now that we've covered the basic gates, I am going to go over truth tables. What is a truth table? All a truth table is, it is a table that outlines all possible combinations of inputs and outputs for the given circuit or logic gate. And when we get further down the line in maybe the next couple videos, it will also cover the next state of a sequential logic state machine. Okay? So, truth table in layman's terms is a table. I'm just going to write it down. A table that shows all possible input-output combinations of a logic gate or circuit, and later on sequential circuits. Okay? A truth table is a table that shows all possible input-output combinations of a logic gate or circuit. Okay? In the case of our AND gate, The way we're going to construct our truth table is with a little help. Okay? So, what we need to consider when constructing our truth table is we're going to need to know our inputs. So, we know an AND gate has two inputs. In terms of our truth table, the rows of our truth table are going to be equal to 2 to the power of our inputs. So in the case of the AND gate, it's going to be 2 to the 2 since there's two inputs. So we know there will be 4 rows or 4 possible combinations with numbers ordered 0 to 3. Okay? So in drawing this truth table, we're going to draw our inputs. We're going to draw our output. Now we know there's 4 possible combinations, numbers ordered 0 to 3. The easiest way to draw the truth table is to first write half zeros, half ones. In this case, because we have 4 rows, it's going to be 2 zeros, 2 ones, and then we're going to half that value. Okay, so it'll be 0, 0, 1, 1, 0, 1, 0, 1. If you're paying attention, you'll realize that this value corresponds to 0. This value corresponds to, sorry, this value corresponds to 0. This value corresponds to 1. This value corresponds to 2. And this value corresponds to 3. Okay? So, for our AND gate logic, 0 and 0 is 0. And this is also similar to multiplication, okay? 0 and 1, 0. 1 and 0 is 0. 1 and 1 is 1. Okay? In terms of truth tables for our NOT gate, or not gate, for our OR gate, okay? So we know that our OR gate is going to produce a value of A or B. We know that our OR gate has two inputs, and we know that our combinations equal 2 to the power of the inputs, which will equal 4. So we're going to construct our truth table again with inputs and our output. We're going to do 0, 0, 1, 1, 0, 1, 0, 1. We know that 0 and 0 is 0. We know 0 and 1 is 1. We know 1 and 0 is 1, and we know 1 and 1 is 1. This is the truth table of our OR gate. And now for our NOT gate. For our NOT gate, we're only going to take one input, or our inverter. So our combinations will be 2 to the power of 1, which is 2. So because our NOT gate only takes one input, we're going to have X, we're going to have our output, we're going to have 0, we're going to have 1. If we input a 0, it'll be 1. If we input a 1, it'll be 0. Or similarly, if we input A, it'll be A prime or the inverse. And yeah. So this is the basic functionality of all of our gates and the basic construction of truth tables, okay? The next thing we're going to go into is some circuit basics and some university level practice questions. Okay, so we're back, and for this portion, we're trying to read combined logic. So, what I'm going to do is for this combined circuit, we have 3 inputs. I am just going to go over those 3 inputs go over what gates they go into, go over what the Boolean expression is for the output of this circuit, and then we're going to construct the truth table, and I will work through some questions. So, first off, we have input A and input B that go into an OR gate. We know the output of an OR gate is always going to be A or B. Okay? Now we have our C input going into a NOT gate, also known as an inverter. We know that the output of our inverter will always be that variable primed. So in this case, it'll be C prime. Okay? Both of these are going into an AND gate once again. So what's going to happen is that it's going to be this variable and this variable. So what's that gonna look like? It's gonna look like our output will be C prime A plus B. Okay? This is the output of our Boolean expression. It could also similarly be shown as A plus B C prime. Okay? So, how are we going to construct our truth table? For this circuit, we have 3 inputs, which means that our combinations are going to be 2 to the 3 or 8, which means we're going to be representing numbers 0 to 7 in binary. Okay? So let's just get our truth table started. We are going to have 3 inputs, 2 intermediate steps, and our output. Okay? So we are going to have A, B, C. Then we are going to have A plus B as one intermediate step, and then C prime as another. And then we are going to have our output Y. Okay? So in terms of our truth table, we know we have 8 possible combinations and numbers numbered with the binary number 0 to 7. Okay? We are going to do 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4, 5, 6, 7, 8. If you guys pay attention to your binary numbers, this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and this is 7. Okay? If you memorize the table from last video, you will recognize this. Anyways, so basically all we're going to do is we are going to just read our truth table and the values we've created. So A or B, or A plus B, 0 plus 0 is 0. Okay? 0 or 0 is 0. 0 or 1 is 1. Okay? 0 or 1 is 1. 1 or 0 and 1 or 0 are both going to also give us 1. And then 1 or 1 and 1 or 1 are also going to give us 1. C prime is going to give us the opposite of each of these values because that's what a NOT gate does. It inverts the values. So instead of 0, 1, 0, 1, 0, 1, 0, 1, we're going to have 1, 0, 1, 0, 1, 0, and 1, 0. Okay? Now, we know that our output Y is A plus B and C prime. So all we're going to do is we are going to AND these two values together. So 0 and 1 is 0. 0 and 0 is 0. 1 and 1 is 1. 1 and 0 is 0. 1 and 1 is 1. 1 and 0 is 0. 1 and 1 is 1. And 1 and 0 is 0. And this is the correct truth table for this binary circuit. So all I'm going to do next is I am just going to do 2 example questions that are university level, and then that will be it. Okay, so for our first question, we will be drawing the logic circuit using only and or not values or not gates, sorry, for this circuit here. AC plus A prime B prime plus B prime C. So the way I first like to get this started is I like to write all of my variables A, B, and C. Then what I tend to do is I tend to create A naught and B naught. So whatever variables are inverted, I also just tend to create those first. Okay, so we have A and C. So we have C and we have A. Anytime you're taking a wire out, you are going to put a circle and a line. That signifies I'm branching off from that A wire. So we have A and C. I need A prime and B prime. So I'm going to take a wire and I'm going to take a wire, and this is A prime and B prime. Now we need to do B prime and C. So what I am going to do is, this hopefully doesn't confuse you guys, I'm going to take a wire from C and extend it down, take a wire from B prime and extend it down. And this is our third AND gate. And now we have these 3 totals being ORed together in a 3 variable OR. So these outputs will go like so, and like so, and this total will equal G. Okay? Okay, guys, so for our final question, a digital system has 3 inputs, A, B, and C, and 1 output, Y. Y equals 1 when A equals C or A and B equals 1, and all we need to do is construct the truth table. So let's remember that our possible combinations is 2 to the power of our inputs, which is 3, which equals 8 possible combination or rows labeled 0 to 7 in binary. So let's just write out our inputs, our intermediate steps, or conditions that need to be met, and our output. So we are going to have 0, 1, 2, 3, 4, 5, 6, and 7. You can also do it as 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. The only reason I didn't do it in that way is because every single time I do it like that, I just always mess up the alignment and it just completely messes me up. So we're just going to go through our conditions, and if either or condition is met, then our Y value is 1 or true. So, does A equal C? Sorry. Does A equal C? No. Oh, sorry, it does. No. Yes. No. No. Yes. No. Yes. Does A and B equal 1? No. 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 Yes. Yes. Okay, now if any of these conditions are met, our value will be 1, and that is the same as just ORing the value. So, condition met, not met, this has been met, not met, not met, has been met, and has been met. So right here, this is the truth table of our output. This is the truth table of our whole circuit. If you used sum of products, you could actually get the Boolean expression and draw the circuit that actually applies these conditions. You could also use K-map simplification, but that is for another video. Thank you guys for watching, and I hope all of you guys have a wonderful day.